Yeah, okay. So welcome to the last lecture. Thanks for coming, especially those of you who are holding out to the very end. So traditionally in this course, well, there's not a long tradition, but this is the second year. And so what we've done, so over the most of the course, we've focused, most of the course is focused on presenting an overview of information security and privacy problems and current current best practices for dealing with them. In the last lecture, we've decided to we take a somewhat different direction and look at some relevant research, a little window on some research in this space, security and privacy, and of course, since I happen to have a particular focus on distributed and decentralized systems, we'll kind of focus on that, on some of the research that my lab has been doing in this space, as well as highlighting on some other interesting challenges and problems in this space. So the plan for today, and so this of course changes every year. At least the details change. So for the first part today, I'll be giving kind of a high-level overview of some of the research my lab has been doing in related to blockchains and cryptocurrencies. And then in the second half, after the break, some of my group members will do some brief deeper dives into a few of the topics here. So again, this is kind of very emerging, just a sample of emerging problems and technological directions in this space. So I hope you'll find it interesting. In a couple lectures ago, we talked about blockchains, of course, and I'll get back into that as kind of to refresh your memory on that topic. But first, I just wanted to briefly provide a summary on what the mission, what my lab focuses on, to give you some context for what we do in this space. Basically, the name of my lab is DEDIS, Decentralized and Distributed Systems, and that's the focus, basically on distributed systems, meaning distributed across networks, but also decentralized, meaning no single points of failure, trying to build systems in which you don't have to trust any particular party, and in which we try to move from the traditional weakest link security problem model, where you only have to compromise one party or node in order to compromise the host system, into what I call a strongest link security model, where you would have to compromise several parties. And so you can already probably see the relevance, the reason I'm interested in blockchain and that my lab has been doing blockchain research, because this model, this strongest link security model, is very key to the way Bitcoin and some other blockchains are designed. So I won't. I'll skip over some of the. I'll just go quickly. And since I already introduced blockchain and discussed it in general in a previous lecture, I won't get into a lot of detail here, other than to note that, of course, it's a very popular hot topic, as you've noticed, and as I can tell, confirmed from the number of interesting questions that you all asked during the blockchain lecture. I'm glad it's an interesting topic. It's very interesting to investors as well. It's kind of creating, the amount of investment in this space has been growing really exponentially over the past few years at a ridiculous rate, and even creating kind of a new form of investment known as the ICO, or initial coin offering, which I won't be focusing on here, but is a very interesting, fascinating topic as well. But of course, this was all kind of launched by Bitcoin in 2008, which I already introduced previously, the first basically successful decentralized currency that creates this notion of value based on information ledgers, based on a record of who owns what, whom owns how many Bitcoins on an abstract ledger that we called a blockchain increasingly. So, the basic distributed ledger concept is unlike having a traditional bank where you trust a single party to record who owns what balance in some currency. That's an old reliable way to do things that Switzerland has been especially good at for quite a few years now. But the idea here is we want to decentralize the blockchain so that many people keep copies of the ledger and check each other, right? And so I introduced the basic Bitcoin blockchain structure earlier, so I won't explain it again. But now the motivation for why do research in this space? Why spend time working on new things in this space? Well, one of the big reasons is the current blockchain systems like Bitcoin and Ethereum and various other systems are very promising in certain respects, have very interesting power and capabilities, but they also suck. They have really severe limitations in many respects. Things like consistency, very slow transaction commitment, low throughput, and horrible energy use and other things. So I'll cover some of those limitations and some of the ways in which we and other groups around the world have been exploring how to rethink blockchain systems in order to try to fix these. Okay, and so I'll organize it, and as usual, feel free to stop me and ask questions if anything comes to mind. As usual, so I will cover basically three basic classes of problems or key challenges in building these kinds of decentralized systems. First of all, the basic way that you secure and organize, you coordinate decentralized groups of nodes. There's a lot of hard problems in that space and a lot of continuing work. Then how do you decide who's a member of a distributed or decentralized system and who gets voting power, consensus power, and things like that? Another very fundamental challenge. And then on what basis do you govern the operation, the continuing operation and evolution of the system in the long term? And this is a challenge that I don't think any current blockchain or cryptocurrency or decentralized systems of any kind has really solved yet. And so you could say that third category is the most open, unsolved problem. Okay. So let's first look at secure coordination and making that scale. So we've looked at, in previous lectures, some of the standard principles this is based on. The distributed trust principle, which underlies Byzantine consensus, algorithms, threshold cryptography, and so on. The idea that you can create, the principle of designing algorithms that can have a number of members, and even if some threshold of them are malicious, not only fail but actively malicious, you can effectively ignore that and figure out how to make the system as a whole behave honestly and correctly despite that malicious behavior, right? And so this concept is very old in computer science and cryptography literature. We've had consensus and Byzantine consensus around for decades. We've had basically all of the components of Bitcoin, all the pieces that Bitcoin was built out of, including the proof of work part and the idea of electronic cash. Those were also old in various respects, but it put together things in a new and different way. And so Bitcoin was very interesting, not so much, it didn't invent any of these distributed trust principles, but it put together a practical protocol out of these existing components in a very new and different and interesting way. And the two most important interesting features, the combination I think that was most interesting, was first that it was open to anyone who wanted to participate, at least in principle. And this, it had at least a semblance of a solution to the Sybil attack problem, namely the problem that all decentralized systems have had, that you try to allow anybody to come and participate, and then you try to build reliable structures, reputation systems, you try to build a currency, anything with rules that have to be enforced, and then you run into problems that anyone who can come and create an unlimited number of accounts or create a lot of fake nodes, a Sybil attacker in general can do really bad things that are really hard to protect against. So huge unsolved problem. Bitcoin had kind of an interesting solution to that in its proof of work. And then the other interesting thing it had was some significant degree of scalability. Most prior Byzantine consensus algorithms and deployments were done at across, say, 4 nodes or 7 nodes, or very, very small numbers of participants, and only really experimentally. Bitcoin came along and basically said, hey, let's not only open this up, but make sure the protocol scales to thousands or tens of thousands of participants participating in this consensus process, which was very cool, how it showed that you could do that. Unfortunately, this very clever, interesting combination of features that Bitcoin bound together also conflated a number of important concepts, such as membership versus consensus, the notion of how to answer the question, who's a member and how much voting power does each member get, from the technical problem of, okay, given a set of members and a set of voting power, how do you arrive at a consensus decision, make a consensus decision, and make sure everybody knows what the state of the universe is? So that's consensus. Conceptually very separate from membership, but in the Bitcoin and cryptocurrency community, they're often confused with each other, in part because they're really closely knit in the Bitcoin design. And this has created not only a lot of limitations, and a lot of confusion. And this is because of the way Bitcoin's so-called Nakamoto consensus model works. And I already went over it in the previous blockchain lecture, so I won't go into too much detail, but the way I like to look at it is it works by making miners play a crypto lottery by printing their own lottery tickets, hashing them, taking a cryptographic hash of them, and trying to do that over and over until they get a winning ticket, namely a ticket with a sufficient number of 0 bits at the end of the hash, right? And so that's a cryptographic lottery. And then, like we discussed earlier, whoever wins a ticket gets to add a new block, you know, at that time, and they announce it, and hopefully their block wins, you know, gets announced quickly, and everybody starts building on their block. But that doesn't always happen, and so probabilistically, sometimes two miners can create competing blocks at once, and you don't have consensus there. You temporarily fail to have consensus because some nodes on the network think that, you know, branch A is the true history, and other nodes think branch B is the true history. And nobody is really going to know for sure until later, when the system probabilistically converges, right? And it converges with high probability over some number of additional blocks, because if you know, when we have a fork in this situation, you know, some of the nodes in the network will be working on extending block A, others will be working on extending block B. One of them will probably win before the other, a reasonable amount of time before the other ones with some reasonable probability. Then everybody on the shorter chain jumps ship, right? So you already know that, more or less. The problem with that, so I want to focus on the problems that creates, and in turn, the interesting, fun research challenges that entices researchers like me and my group with, right? So of course, because this proof of work process paces the blocks by, you know, 10 minutes on average in the case of Bitcoin. In Ethereum, it's shorter, but it still has to be reasonably paced. It takes quite a while to commit any transaction, even with this very uncertain, you know, single block kind of thing. If you really want to be sure your transaction is committed, you've got to wait several blocks. 6 blocks or 1 hour is Satoshi Nakamoto's recommendation. And then there's also the problem that since all of these miners, all of the validators are rechecking everything that everybody else is doing, the overall system throughput does not increase with the number of participants. It stays absolutely the same regardless of the number of participants. Maximum about 7 or 4.5 transactions per second, depending on how exactly you count. And this proof of work turns out to be a huge energy disaster, right? So let's first look at this scaling problem. The problem, you know, so, you know, Bitcoin can handle a ridiculously low number of transactions per second. How can we increase that? Now, there's, you know, many ways to increase, to, you know, to scale blockchains and cryptocurrencies. You know, the Bitcoin core people are focusing on one aspect, and different groups are focusing on different ways. We can't cover all of them. So we'll focus on the approaches that the DEDIS lab has been exploring. And this kind of started with a project we did a couple years ago, published in Usenix Security 2016, called Bizcoin. And the idea, and this in this paper we managed, so I won't, you know, try to present all the details. You're welcome to look it up if you want to see more information. But the high level is we showed a way, certainly not the only way, but one way to combine Bitcoin type architecture with classic Byzantine fault tolerance algorithms in order to get immediate permanent transaction commitment. So you know when you commit a transaction, it stays committed, not just probabilistically, and a couple orders of magnitude higher throughput as well. So how does Bizcoin do this? Well, first of all, it builds on other research elsewhere. This is, you know, a very common practice. Most research is, you know, research never lives alone or you know, kind of or starts from scratch. We always build on other people's interesting work elsewhere. And in this case, the most closest, most relevant prior work that we built on was a design called Bitcoin NG from Cornell. How many of you have heard of Bitcoin NG before, out of curiosity? No? Okay, so this is unfamiliar territory to you too. So Bitcoin NG took the really nice step of finding a way to deconflate, to separate in the Bitcoin, to take the Bitcoin architecture, but separate the notion of membership from transaction commitment or consensus, right? So like I mentioned, Bitcoin conflates these two notions. Transaction, so member, figuring out who has a right to membership at a given time is completely tightly coupled with how transactions are committed. And Bitcoin NG finds a way to decouple those two concepts. Yeah?
What do we mean by membership? Because Bitcoin anyone can take part in the mining process of the blockchain, right?
Yeah, yeah. So yeah, I should probably have explained that a little more clearly. Imagine a version of Bitcoin in which you just in which Satoshi Nakamoto hard-coded in the code the public keys of 100 of his friends. And the code, and the Bitcoin code just says, okay, these are the 100 miners, and that's a fixed closed group. This is going to be a Bitcoin cryptocurrency among these miners, and you want to add you want to add or remove any miners, you're going to have to change the code, right? Because that's the membership. Now, if you did that. Well, modulo some caveats. If you did something like that, you wouldn't actually need proof of work at all. So you could, there's actually many alternatives. You could, in principle, run a classic Byzantine consensus protocol among those 100 validators. And you don't need proof of work. You don't need all this wasted energy. You just have the consensus work that way. You could also, if you want something like proof of work, but among, if you want Nakamoto consensus, but you have a closed group and some way to get let's say a trustworthy independent time source of some kind. If you have a trustworthy source of membership, let's assume you also have a trustworthy independent time source. And then you could use that to seed a pseudo-random block leader election mechanism that would produce the equivalent of the crypto puzzle answers without actually needing to invest the energy, right? So there's a lot of potential alternative schemes. The point is the reason Bitcoin needs wants the proof of work at all is because it wants the open membership structure. It doesn't want to just set a fixed set of miners like all the classic Byzantine consensus protocols and the distributed systems theory had assumed would be there somehow, right? So, yeah, so creating that openness, to constant membership flux in the membership, it was a very interesting, success in a way. But the way those two concepts were coupled in the Bitcoin's architecture, creates a lot of problems too. And Bitcoin NG basically took a first step toward figuring out a way to decouple those concepts while still retaining something that works and that has a lot of properties of Bitcoin. And the idea is you still use proof of work in Bitcoin NG or Bizcoin, but you now have two types of blocks. One type of block called key blocks are only for proof of work, and those serve a leader election role. So Bitcoin already has, in Bitcoin, you know, each block effectively serves a leader election role already, in that any block miner, the moment a miner gets, you know, solves one of these crypto puzzles and gets to add a block to the blockchain, that act elects them leader for one block, for, you know, a very ephemeral notion of leadership. And they get to do nothing else other than announce that one block. That's all that, you know, the miner of a block in Bitcoin gets to do as leader, but they can prove that they're leader for that one block by just announcing the block, right? Now, Bitcoin NG says, okay, well, we have this leader election mechanism based on proof of work. Let's let the leader use their leadership, their proof of work based leadership, for a little longer. Not just for one action, but maybe for several actions, right? And so Bitcoin NG proposed this idea that after each key block, after each of these proof of work blocks, the leader could then, so the key block would basically not necessarily commit any transactions immediately, but it would say, it would just be purely a leader election mechanism saying that would allow the successful miner to say, hey, look, I'm the leader now. I have the latest proof of work block, and therefore I'm going to be committing transactions for the next 10 minutes, but not all at once, but actually spread out over the next 10 minutes, right? And so the leader basically gets to announce their leadership and along with their public signing key, and then they can, over the next 10 minutes or however long until the next leader supersedes them, they get to commit a series of transactions just by signing them with their private key. And so the actual microblocks containing the transactions just have a simple digital signature from the current leader matching the public signing key in the latest key block, right? And so, you know, so the idea is, so this resolves one of the important tensions in the Bitcoin model, which is that we'd like to make these proof of work blocks much faster, much closer together, but you can't without defeating the security that the proof of work mechanism provides. You really have to keep them far enough apart so that the announcement of each new key block can propagate widely in the network so that we don't have too many of these multiple histories, multiple leaders, you know, situations. But we want transactions to be committed very quickly, much more often, and this in principle provides a way to do that by allowing, you know, an existing leader to commit many transactions or many blocks, smaller blocks worth of transactions successfully between leader elections, right? So this is a cool idea, and some experimental blockchains out there are actually using this. It does have the downside that you're still it adds some complexity and some technical and security challenges. And when one leader is the leader, you're still kind of completely reliant on that one leader and that one leader alone to being honest and playing by the rules. A malicious or failed leader can do a limited amount of damage, but you're still kind of relying on that one leader for this period of time. So that brings us to the question, can we bring classic consensus algorithms back into the picture? And that's what Bitcoin, some of my group's work, tries to do. This builds on the classic consensus protocol that I mentioned earlier, I believe, practical Byzantine fault tolerance, the Castro-Liskov protocol, which is a very mature protocol, but like most classic consensus protocols, it assumes there's a closed group of participants that's well defined. You know, these are the members, and it's a closed and typically traditionally small group. Usually the experiments with these protocols are done with at most tens of nodes, not hundreds or thousands. and it's not necessarily easy to make them scale. So, so Bizcoin tries to, so what Bizcoin does is keeps Bizcoin's proof of work, but, and it leverages the Bitcoin NG ideal of decoupling leader election and membership from consensus, but it repurposes proof of work to give miners temporary shares in a sliding window of consensus group members. So at any given moment, so in Bitcoin NG would be kind of like this, but a sliding window of size 1. So a Bitcoin NG would provide a constantly rotating set of autocratic dictators who, for a brief period, get to completely dictate what gets committed. Whereas the idea of Bitcoin is that we don't want to ever have an autocratic dictator who decides everything, but instead we always want to have a consensus group of some reasonable number, like 100 or 1,000 miners representing a proportionate fraction of the recent hash power invested in the system, right? So yeah, so every time a miner manages to get a new proof of work, they basically get a ticket, get rotated into the window. Somebody at the end of the window gets dropped out, gets rotated out, and so you always have this more or less gradually rotating share of consensus group members. And then we run more or less a classic Byzantine consensus algorithm among those group members in order to actually commit the transactions. And that way we can actually, since the classic BFT algorithms are reasonably fast, they don't need to wait for proof of work stuff. They can run as fast as the network allows. They can complete a transaction commit once just every second or two, every few seconds, and therefore commit many transactions, many blocks worth of transactions between any two proof of work events or any group rotations. Yeah.
Has this been applied in practice?
So we have an experimental prototype, and a number of startups have been using this in their white paper designs. I don't know to what extent they, so the experimental code is working. It's not deployed in a cryptocurrency you can buy and trade yet, publicly. A bunch of, several startups seem to be developing, cryptocurrencies and blockchains based on this for public deployment. But I don't know their status, how far along they are in terms of that. I'm not aware of any that's actually deployed and operating based on this yet. But I think there is one that's actually operating based on Bitcoin NG, but it's a long pipeline. So I expect we'll probably see some before too long. Yeah. So, okay, can you be more specific?
Yes, so this window of size W,
yeah.
This is over the...
So these are the key blocks, the proof of work blocks. So every time a miner succeeds in solving a crypto puzzle, just like in Bitcoin, the miners are trying to solve crypto puzzles, they get to add one new key block to the blockchain, right? And everybody can see, and so this key blockchain is just like a Bitcoin blockchain, but it doesn't actually include any transactions in it. It's just a set of, each key block just says, here's a proof of work, and here's the public keys, signing key, the identity key of the miner who got it, right? And so each of these key blocks is just serves as a temporary ticket saying, I'm a member of the Bitcoin consensus group, right now, you know, at least as long as I'm in the window and as long as the chain hasn't grown so to push me out of the window, right? So every time someone gets a new key block, this window shifts over one, right, to include the new member and to eliminate some old member, and you know, the size of the window is just a design parameter. We used like 100 or 1,000 to represent the last the last day or the last week worth of minors, right? And so the reason, you know, the reason we want this to be a window is because we want the members of the consensus group to be chosen in proportionately to the amount of hash power, right? So if over the last few days 10% of the hash power has been contributed by some particular mining pool or some particular operator, then that operator is going to statistically, on average, get about 10% of these key blocks in the recent sliding window. But then if they stop operating, then, you know, the window is going to slide past them, and, you know, eventually they'll get their tickets, their membership tickets will get rotated out and replaced by somebody else, right? So in other words, it allows open membership just in the same way that Bitcoin does, using this proof of work competition, and you get the same proportionality. You know, the more hash power you bring, the more share of the consensus power and the more share of the rewards you get, etc. But you get it in a different way. You don't, you know, immediately get a bundle of instant rewards from committing a bundle of transactions just once when you get that block. Instead, you get your block that you get is a temporary membership ticket that gives you membership, you know, for the next in the consensus group for the next 100 or 1,000 key blocks worth of commitments, right? Does that make sense? Okay, good. So that addresses one of the problems that Bitcoin has to deal with. The other that I mentioned is classic Byzantine consensus algorithms tend not to scale real well, or at least to thousands of participants. They get a little slow and clunky. And one of the reasons, if you just look at the communication diagram in the classic PBFD system, especially the prepare and commit phases, you'll see the reason for that is pretty obvious. Basically, in these two most critical phases, basically all of the nodes have to have to sign off to all of the other nodes, attest to each other and convince each other collectively that everything's good. And so in the case of the prepare phase, everybody has to convince everybody else that they have checked the the next block, the next thing to be committed for consistency, to make sure it follows all the rules, it doesn't double spend, it doesn't, you know, try to fork history or change something that's already been committed, you know. So everybody in the prepare phase is checking everything proposed for consistency and convincing everybody else that they're signed off and ready to go on. And then the commit phase is where everybody has first checked that everybody else is prepared. So each node first has to be convinced that a sufficient critical mass of everyone else agrees that this is that the thing where the next block is consistent with history, but also that there's a significant sufficient critical mass, a 2/3 majority, that's willing to remember this fact. And so the commitment part is where all of the nodes basically commit to remember this new block, this new decision. And only then, once we have that second sign-off phase, can you consider a transaction fully committed. So a client relying on receiving those funds can decide, okay, it's committed, it's never going to be rolled back then, right? So Of course, this is a slightly more complicated protocol than Bitcoin, but it does have the advantage of getting that immediate commitment certainty. Once you've done this, under the security model, you know that the transaction will not get rolled back even probabilistically, like in Bitcoin, right? So that's how classic Byzantine consensus protocols work in a nutshell, but they have these more or less all-to-all communication and sign-off phases, which aren't very efficient when n is in the thousands, right? And so because of that, we used some distributed systems and crypto tools to make those processes, the all-to-all communication and sign-off processes, much more efficient. Basically, in a nutshell, we have a leader at a given time. The leader isn't trusted. The leader can be replaced if it behaves maliciously or goes away. But the leader organized these nodes into tree structures, and then we can use we can send announcements, basically broadcast style, redistributing things efficiently among all the nodes, just like you would do in an efficient video broadcast or something like that. But then coming back up the tree, we can cryptographically aggregate the sign-offs. So the leader says, hey, let's prepare this, or let's commit this thing, and then everybody basically cryptographically composes many digital signatures of all these individual nodes into one composite collective signature that then anybody can check directly to see that one small piece of cryptographic evidence that, oh yeah, everybody did indeed sign off on this prepare or this commit, right? So yeah, so that's how Bitcoin gets scalability by it uses PBFT normally, but it replaces this sign-off process with a slightly more complicated protocol called collective signing, but that scales much better. Right? So I see I'm actually going much slower than I had in mind, which is probably okay. We just probably won't get to all of the presentations I had in mind. So just to continue the scaling focus a little bit. So this this improved. This showed we could improve the scalability of a system like Bitcoin, but only to a certain degree. And we still, in particular, have the problem that all of the nodes in this system are basically replicating all the, doing all the work over again redundantly. Everybody is checking every transaction and doing a separate copy of all the work, which means you still don't get horizontal scaling. You still don't get the desirable property that, say, cloud computing does, where if you add more participants, you add more resources, you'd like to get more throughput, be able to process more transactions per second. And so we'd like to get that, and that's the task of OmniLedger, which is a design for scale-out sharding that we actually presented just last week in IEEE Security and Privacy. And the basic idea there is from Bitcoin, we already use these sliding windows to create potentially large consensus groups. But now the idea here is we're going to break up those large consensus groups into smaller ones, managing separate multiple shards, essentially. And we want each of these shards to be big enough to be still collectively secure, but small enough so that we can have at least a few shards in the total system, right? So just to give you a quick high-level intuition how this works and what the challenges are. So let's say we just let somebody pick arbitrarily who's a member of which shard, or let the nodes choose themselves I want to be a member of shard 1 or shard 3 or whatever, right? What would go wrong in that design, that straw man design?
Malicious guys would go to the same shard and then
Exactly. Yeah, a bunch of colluding nodes would cluster in one shard and therefore be able to overcome the consensus threshold within that shard and basically completely break that shard, even if they can't break the whole system. But anybody whose Bitcoin accounts or whatever were handled by that shard would then be completely vulnerable, right? So we want to make sure that if there are any colluding, to whatever extent there are colluding malicious groups in here, we want to make sure they're distributed randomly across the shards and not able to stack any one shard, right? And so one of the critical challenges is making sure we pick those shards in a random and unbiased fashion from the total membership, right? So that's the idea, and for that we actually have to rely on a separate. We build on a separate randomness protocol, which was a separate research project in itself, and that's actually a separate interesting topic. And I'll get to that in a minute as well. But then that's one of the challenges, picking the shards securely. The other challenge is that what if you're paying funds from an account on one shard to an account on another shard, right? Different users are going to have accounts whose state is held in different shards, and a transaction might need to atomically use funds. And in Bitcoin transactions, a Bitcoin transaction can take money from several accounts, combine it together, and distribute it to several other accounts, right? And we might need to combine funds coming from accounts across multiple shards and then distribute those to accounts on other shards. And that has to be all atomic across all of the shards. It wouldn't be good if we could have a situation where a transfer from Alice on shard 1 to Bob on shard 2 completed for Alice but not for Bob, or vice versa, right? That would be really bad. We would either be creating money or losing money. And we don't want either of those to happen. We want, atomic transfers of money, right? So cross-shard transactions are the other kind of major technical challenge that systems like these have to deal with. And so I won't get into all the technical details of that. So my student Lefteris has a talk that goes into much more detail on that we might or might not have time to get to. But anyway, and I'll come back to the randomness protocol. So doing this basically the upshot is by combining this techniques, you get this scale out capability. And you can, but you still have to make a choice. You have to decide how strong an attacker you want to tolerate, that you think is plausible in this context, because that determines how big or small the shards can be. Smaller shards are going to be less secure because it's going to be it'll require an attacker that owns a smaller portion of the network to overcome some shard, the security of some shards, whereas having a large shard gives you a very high probability that an extremely strong attacker won't be able to compromise any one shard, right? So that's a trade-off, but for various, but we showed that for various choices of those parameter, you can get potentially very high throughputs on this testbed environment, and these results are limited by the size of the testbed, they don't represent any particular limit to the size that this could, in principle, scale out to. Okay? Yeah?
Do you actually have 1,800 processes?
No, so good, really good question. So this is an experimental methodology detail that I didn't get into on this graph. In general, it's really hard to find test beds that readily available with 1,800 real separate physical hosts to test on. So in practice, what we usually do in these kind of situations is we use test beds like EmuLab and DeterLab, which allow you to simulate large-scale test beds, but interpose virtual network delays on the links between these virtual nodes, and then we oversubscribe each physical node. We run some number like 32 or 64 virtual nodes on each physical host. So that unfortunately it can inject experimental artifacts, but it's kind of the most practical way we generally have to experiment with large systems. Yeah, you. Yeah. Okay.
In fact, this has a little bit of impact. It's not biased, but it's not exactly the true information, right? Because we don't have the network delay or stuff, right?
Right. So these experiments do account for network delay. The test bed is artificially imposing basically about 100 milliseconds each way among all of the nodes. So simulating a fairly a scenario where all of these validators are really spread around the world. So if we didn't add those delays, it would be much faster. Actually, it would be practically instantaneous, comparatively. So this is already doing a reasonable job at simulating a very large-scale, wide area deployment. Not perfectly, because it's but there's plenty of caveats in there, but it does take account for network delays. Yeah. And those kind of doing experiments that take account of simulating real environments well is actually one of the ongoing challenges in doing good research. You got to do a faithful job of that, but also within reason, within the the testbed resources you have and stuff like that. Yeah. Okay, so that's the scalability focused part. Let's go ahead and take the break that we're already late for, and come back, and we'll decide how to use the rest of the time afterwards. So let's come back in about 5:20. Okay. Thanks.